So this is hacking mobile devices, and we're near the end of everything here. Oh, by the way, a bunch of conferences are coming up. B-Sides this weekend, so I canceled my Saturday classes. I'll be there. I looked, they had interesting talks about AI, so I highly recommend going to B-Sides. And there's a Hack the Bay event on Monday, and the RSA conference next week. Thursday is free college day, so if you go to any of these things, they're worth extra credit, and it should be good for you. The B-Sides cost like $70, but you can apply for like a discount. RSA, I think, is free on college day, and I think Hack the Bay is free. And you can also Google for a free Expo Pass and go to the whole RSA conference if you want to. Just Google for free Expo Passes, and various vendors will just give you one. Anyway, so we're here at 128, and down here, so this is the next to last class. So I'm going to talk about the first part of chapter 3, and the last class is here. All right, that's it. So let me talk about attacking iOS applications, which is here. So we're going to talk about transport security, insecure storage, and Hopper, which is stuff we've pretty much done before in an Android context, and a lot of it is the same. So if you want to attack from the network, then you might be able to send some kind of data from server-side applications. That's one attack scenario where you send bad data through the network to the phone, like SQL injection, cross-site scripting, that sort of thing. Physical access to the phone is another big risk. If you could steal a phone, can you do anything if you get physical access to somebody else's phone, like the police that seize phones or go to a crime scene and seize the phones? And then there's interactive access to the phone. This is where you get to implant malware on the phone. And now you have remote control of that app, so now you can attack one app from the other apps on the phone. Those are common attack scenarios. So transport scenario is an obvious one. If you're loading data over HTTP, this is never safe. You should never use it for any purpose anymore, because even if you're just loading static data, someone could be adding scripts and other things to that data. And almost nobody uses HTTP very much. Only older apps use it, although it is still allowed even on iPhones. I was sort of horrified to find that out. But some older apps do send data over HTTP. It's a very bad practice, however. So you can just, if it's unencrypted, you can just use Wireshark to view the data, or Burp to put it in the middle. And so if you are going to use TLS, which everybody should, then here's how you do it in iOS apps. There's a thing called the URS loading system, another one, the Carbon Framework, and the Secure Transport API. So the URL loading system has high-level methods, very much like the Windows API, URL connection, URL session. This is what most people do. Carbon Framework is another thing you can use that gives you greater control over network requests, but normally a developer doesn't want that. They just want to do something like connect to a website, download the file. And that's what the other framework makes it easier to do. And then there's the low-level API, which is what's actually being used by the others, which has basically the raw sockets. This is what they call it. These are usually the same as BSD, Berkeley Standard, Unix sockets. Very difficult to use directly, where you have to program every packet. You normally want the operating system to do that for you, where you say, go to a website and download a file, and that means send a SYN, SYNAC, ACK, negotiate an encryption key, create a session key, a whole bunch of stuff you have to do, and you just want it to do that all for you automatically. But if you want to, you can control every packet and make some strange network protocol of your own. All right, so certificate validation. As you know, what you should do, first you do SYN, SYNAC, ACK to open port 443, then you get a certificate from the server, which is signed by some third party like Google or Let's Encrypt, and then you should verify that. That's the point of this. This is the authenticity part. By verifying it with a trusted third party, you make sure that you are in fact talking to the real Google and not some fake site pretending to be Google. And then you also have an encryption key, so you can encrypt data, and only the intended server can read it. So it's all based on these trusted certificate authorities, which are very much like the insurance companies of the web. The only thing these companies do is validate certificates, so their product is that you can trust them. So they have high incentive to not deceive you, to not make mistakes and get hacked, and so on. And so that's the idea. So you can allow self-signed certificates if you want to. This is a dangerous thing to do. You normally only do it for testing purposes, where you have certificates that are not verified by a third party. So they do not verify the identity of the server. They do provide an encryption key, but you don't know who you're talking to. So this is not anything anybody should be using in production. But if you want to, you can make an app that does allow self-signed certificates. Browsers will do this. They'll pop up a warning saying, this certificate is not secure. Do you want to go here anyway? You can approve it and then go there anyway, but you should know you're not really being properly protected. So you can do this. You can set up a parameter in the Carbon framework that also allows self-signed certificates. And you can disable the certificate validation entirely if you want to. And the problem is people do this because they want to test something and then they leave it that way in production. When I tested them a few years ago, it seemed to me like maybe 3% or 5% of iOS apps had broken SSL, and maybe 15% of Android apps. A lot of them did. Just mainly because developers just writing their code without certificate validation and then never fixing it, because I think they just set up a test environment and then sent their test version out. Anyway, so here's a lot of problems. Self-signed certificates are ones that are not signed by any trusted authority at all. Expired certificates, host names that don't match the name of the... This happens a lot when a company buys another company. You have a company called like Yahoo, then it gets bought by somebody like Microsoft, and now the certificate doesn't have the right name on it. The page is really now moved to a Microsoft page, but the certificate still says Yahoo. So that's a mismatched host name. You can have expired root certificates, or you can just allow any root certificate without untrusted ones. These are some of the many problems you can find. So the easiest thing to do, as we've done in the projects, is route the traffic through the burp proxy, and then your browser should tell you your connection to this site is not secure. That's what it should tell you when you're going through a proxy, because the burp proxy makes fake certificates, which are not from a trusted authority. So they should fail the test. Now, this affected, the famous case in Apple was in 2014, the go-to fail. Apple had a problem in their code, and the code problem was this. Their code, for some reason, they write C code with goto in it, which I have never done. I thought goto was considered poor style, but they used goto for some ungodly reason. So they enter this function to check the certificate, and they test it for one problem. And if this problem exists, it's creating this, it's going to return this value called error. If the error is 0, the certificate passed. If the error is some other number, the certificate failed. So here, if it's not equal to 0, then you failed this test and you go to fail. If it's not equal to 0, you failed this test and you go to fail, but they have an extra go to fail here. And the problem with C, one of the many problems with C, is that white space does not matter. It does not enforce indentation like Python. So it was not obvious to the developer that this if condition affects only the first go-to fail. The second go-to fail should really be over here. So the result is this if statement says, if this condition is true, go to fail, otherwise go to fail. So it never does this at all. It always goes to fail. And therefore, if you pass the first 2 tests, but you're going to flunk the third test, it will still accept the certificate. So a whole class of certificates with a flaw were accepted, and essentially they were all accepted because this was the most important test. So it was just that one duplicated line there caused the entire Apple device to accept essentially all certificates for a while. So that's a pretty serious flaw.
Was that intentional?
No. It was a serious bug, the go-to fail. And this extra line here was in the Apple code, so it was like a patch, and until the next patch came out, all the phones would just accept every certificate.
Shaky fingers.
Yep, and this happens a lot. I mean, when I first taught the advanced hacking class, maybe 10 years ago, we used Solaris, and at that time, Solaris had a vulnerability that if you used rlogin to log into another server as root, it would accept any password. It never checked the password at all. Anybody could log in as root anywhere, anytime. And I was stunned. This kind of thing. These things happen. Amazing things happen.
Because different machines load up different software.
Yeah.
If you want to run that software, you should go there full privilege. So you run your stuff, and you go to another software, another program, you run this stuff. That's the reason to do that.
Well, but you should have a valid password for any device you connect to.
But that way you slow up all the work.
Well, yeah, but this was not for that reason. However, that, by the way, is the justification given for, there is a AI product that has this, there's a product used to do load balancing of AI clusters, and it has no authentication at all. Every request is just honored, and they tell you never connect it to the internet, but thousands of people do. And if you do, of course, anybody can use your stuff. And they say it for this reason. They say it's supposed to be a load balancer, it has to be fast. We deliberately built it with no authentication. It's your job to isolate this network, but people don't isolate it.
There's no way to set up, because the one group of engineers, they go together, and then they want to do work fast, that's a way to set up.
Yeah, but if you do have a thing like that, you have to have good documentation that explains to people how to deploy it, and they didn't. Anyway, that's the kind of thing tends to happen. So that's the go-to fail. And so there are many other SSL errors you can make if you're using the framework. It's harder to make these mistakes if you use the high-level API that just makes the whole connection with one statement. There's not many adjustable parameters, so you can't usually set it to a low-security mode. So these you can modify the protocol version it's going to use. You can, in principle, tell it to use SSL version 2 and SSL version 3, even though both of these have been deprecated and abandoned years ago because they're not secure enough. So here you can in principle specify these old versions, but you shouldn't use any of these. Even TLS version 1 should not be used anymore. These are all old. And here's ones that allow you to have totally insecure sessions, security level none, and so on. Here's more settings that can have vulnerable versions. And the preferred setting is TLS 1.2. Now, it would probably be even better to use 1.3, but 1.2 and 1.3 are both very good versions of TLS. So when you connect to a server, you send a SYN to port 443. The server sends back a SYN ACK. Then you send an ACK, and then you send a client hello. And that includes this here. This is the client hello. So you tell the server what kind of browser you are and say, I could talk these encryption routines. And so if you are really running like Windows Internet Explorer on like Windows 95, then you only have really old, really insecure crypto suites or MS-DOS or something. So this is a modern browser, so it has a lot of good things here. Elliptic curve Diffie-Hellman. So you tell the server, I can speak these protocols, and the server chooses one and says, okay, let's speak this one. Or the server says, no, I won't allow you to use any of those because you're a really old browser, and I will not talk to you because you will not support any secure encryption. That's the issue. So marketers have pressure to accept everything, even really old things, because they don't want to turn away any customers. And that's the decision you have to make as a developer, is are you willing to lose the business from people with really old stuff in order to have high security standards? Because if you don't, then everybody can be downgraded to those insecure protocols. And there have been protocols so bad as to use like 40-bit keys, which can be trivially cracked in a few seconds. So, all right. So a developer can specify an insecure suite. In principle, you can write apps that do use insecure cryptography. It's just not a good idea, of course. And, all right. And you can so when you intercept encrypted communications, you use burp, and it gives a fake certificate, and then you have to tell your phone to trust that fake certificate. Now, if you have certificate pinning, that means your app has an extra test above and beyond the normal certificate verification. It has a built-in test to do something like make sure the certificate comes from the specific trusted authority you specified. So if that's the case, you have to bypass it if you want to intercept the traffic, because there's no way you can get the burp certificate to pass that test. So you use substrates, which are like Frida that we've used on Android. There are various substrate tweaks that will modify the iOS operating system on a jailbroken phone so you can overcome the certificate pinning. All right. And then there's insecure storage. I've gone back and forth on this one. For a while, I used to audit a lot of Android apps and some iOS apps, and I would test them for storage and for network transmission and for logging insecure things like passwords and turn them in. And I finally stopped reporting insecure storage on iPhones. Or here's the idea. The idea is if you store something sensitive like a password on the phone, then if somebody steals your phone, they can get in. But they would only be able to do that if you get in your phone while it's unlocked. Because as we talked about, the encryption on Apple devices is really strong. So if your phone is locked, they need your PIN or they're not getting in. The data is encrypted. So the chance of them being able to get the data off the phone is pretty small, but only if they're able to somehow get in, like the Touch ID sensor, or to find some exploit, or find a jailbroken phone with default credentials like SSH Alpine or something. These are all the cases, will somehow bypass it, or you can pair with a malicious computer or exploit the boot chain. These are the only ways to get in. But those are pretty rare, although Cellebrite claims they can do it. They claim to sell you a device that can hack into any phone and get in anybody's account by bypassing the login, but there are no public free exploits that will do this on most phones. So if you store things in plain text, or you use custom encryption with an insecure key like most of the apps I tried that make some kind of private key in some way and store it on the phone somewhere where they think you can't find it, or stored with the wrong data protection class. These are possible ways data can be stored wrong. Remember, all this encryption stuff. The passcode comes in to be mixed with the device key to make the passcode key, and everything's encrypted with that. So if you don't have the passcode, you can't get at any data that has any protection class at all. And there are protection classes that are completely protected until first user authentication, and none. So you'd be able to get here. If you don't have the passcode, you could still get this stuff, because the device key is enough to get in there. So you can make things that are available to anybody, and so you could, I suppose, make the mistake of storing important data with this class, but that would be a pretty ridiculous mistake, to deliberately not use the protection classes. If you use either of these, then nobody's getting in there, unless they have an exploit that can bypass the login on the phone. So that's no protection at all, not encrypted, complete until you first log in is the normal case, but that's discouraged for sensitive data. And all right, if data can be backed up, then you can make a backup, of course, but again, you have to have the login for the phone to do it. And there's keychains, which is where you should be putting sensitive things anyway. It creates encrypted stuff with the operating system. Just like on Android, there is an encrypted system to stick your private stuff in if you want to, and you should just learn how to use it if you want to store secrets on the phone. So with dynamic analysis, you can test on the phone to see if there's stored data. I just do it with command line tools like grep, search through the file system for a stored password. Okay, and then you can modify iOS applications with Hopper. Now, I had a project, I didn't include it this semester because it was really hard, but you can, in principle, get an iOS app by dumping it from a phone, because apps come encrypted from the store, they're decrypted on the phone, and on a jailbroken phone, you can copy them from memory and extract the app and get a decrypted copy. And then you can disassemble it with Hopper, which is just a disassembler like IDA Pro specifically for this purpose. And so you'll get down to the actual assembly code here, which is this will Intel assembly code for your app. And over here you have the names of the methods and such, app delegate, view controller, and so on. And so you can have a jailbreak detection here. This device is jailbroken. Please remove the jailbreak and try again. So here's the code that calls this thing. This is the assembly code that does this test, and here's the message when it fails: security violation. So, you can observe it, but it's just like disassembling x86 code, compiled to assembly code. It is not written in Java. It's not very easy. And you can also create pseudocode. Hopper has this ability to decompile and turn it back into something like C. So you get this kind of result, which is the same thing you would get from Ghidra these days, although I don't know if Ghidra does iOS apps. It might. But anyway, the hard part is getting the app itself off your phone. You really need a jailbroken phone, and then you put the app on there. And it can be done, but it's pretty difficult. You really need a Mac and a jailbroken phone, and everything depends on the version of the phone, the version of the iOS, the version of the Mac, and so on. So it's really not practical for teaching in a class like this where people are using random home devices. Not everybody has the same device. Anyway, let's try a Kahoot. That was 3A, so I should have, there it is, 3A. Good. I changed the music. I'm more disoriented now. All right, so what attack scenario would require putting malware in the App Store? That's called interactive, where you get a malicious app that can then attack the other apps on the phone. It's not very common. It's hard to get malware in the App Store. That's Apple's justification for charging everybody such a huge fee to be in the App Store. They say that's how they can afford to keep it so clean of malware. But anyway, that's changing in Europe now. In Europe, you have to load stuff from other less trusted stores. But I don't think it's operative yet. All right, what implementation is most commonly used? URL loading is the same in Windows. The Internet Load URL, the WinINet library, is the high-level one that will just have a whole communication with the server in one command, and that's what a normal developer wants. Both of these give you low-level control, which you usually don't want, to make you worry about every little thing. This is the one that's high-level and the most normal for a developer to use. All right, you install Burp, but you can't intercept network traffic, so what would be wrong? It must have certificate pinning. If you installed the Burp certificate, but it still won't accept it, then the app must be using certificate pinning, which requires other tests before it'll accept the certificate. So you'd have to bypass that by instrumenting the operating system. All right. How do you get user data from a stolen, locked phone? This is almost a CISSP level question. Okay, that's interesting. I was thinking, these are all pretty unlikely. I would think, these days I would probably say no way is probably the best answer. If there's a way to bypass the touch sensor, that would be nice, but there usually isn't. This is kind of unfair. This is why these things are extra credit. It's this one particularly bad. I don't like this question much. I'm going to try and remember to remove it. Anyway, these are possible ways to get in. CheckRain, by the way, won't do this. They won't bypass the login code. They deliberately avoided that because the jailbreak people didn't want to help criminals steal phones. So trying many passcodes manually, in principle, could work, but you're going to need a special device like a gray key to do it if you're not going to lock the phone by guessing too many. All these are really hard. I think I would say there is no way is probably the best answer. Anyway, I can't change the grading now, but I'll try and remember to change that next time. Anyway, the purpose of these things, the server's review is still there, and that's why they're extra credit, because these cahoots are sometimes pretty unfair. And that last question, I think, was not very fair. Okay. So, close this and stop the recording.